continuous. It's just that my box is finite. Remember, I've coarse-grained everything. And now I can write it as integral. Besides, it doesn't matter whether it's an integral or a sum, as long as the function is slowly varying. Right? Which one?
This phi is equal to this Fourier transform.
Yeah, eventually we will. When it's convenient. Okay, we will do that. But first I want to really write it as a matrix, because people are used to having a matrix with discrete indices, right? So K are those indices. Okay? Good? So now you have that, and of course there's also this other term, phi squared. You do exactly the same thing, it doesn't have the derivatives, right? It doesn't have this part. So it will be phi tilde of K1, phi tilde of K2 without this, the same integral over x. So basically your S of phi is nothing other than 1/2 the sum over K squared plus M squared, phi tilde of K, phi tilde of minus K. Okay? So you've diagonalized. Okay, almost. Not exactly, because really the matrix that I showed you over there was the same x. It was not x star times x. Right? What do I mean by x star? Well, look, this guy, this phi is a real field. So if I take its complex conjugate, it should be the same, right, as the field itself. So this tells me that when I take a complex conjugate on this side, this will become minus, this will become phi tilde star. So this tells me that phi tilde star of K is phi tilde of minus K. Right? So if I define two real variables here, so if I define phi tilde of K is phi tilde 1 of K plus I times phi tilde 2 of K, both of these being real fields, then I only need half the set of K's. Okay, what do I mean by that? What I mean is the following. So what I mean is that phi 1 tilde of K is the same as phi 1 tilde of minus K, and phi 2 tilde of K is minus phi tilde 2 of minus K. So if I know phi 1 tilde and phi 2 tilde for half the values of K, I know it for everyone. Okay? So in 2 dimensions I can certainly draw something like this. And here's Kx, let's say, and here's Ky. Then I'm going to just look at the values in this region. If you want to be really, really nitpicky, you also include this. Okay? And you don't include that. All right? But that's really a detail. All right? So that's what it is. So you have basically half the values of K, and you have two variables. And these are now real variables. And this phi tilde of K, phi tilde of minus K, I can therefore write as phi tilde 1 squared of K plus phi tilde 2 squared of K. Right? And now everything is like that. Well, I have erased it, but everything is like that matrix that I have. Okay? Good? One last thing. Remember, my integral was really over all the values of phi of x. But Fourier transform is a unitary transformation. So the Jacobian of that transformation is 1. So the product of all the d phi of x's is the same as the product of all the d phi of k. Alright? Good? Okay. So now we know this matrix, we've already diagonalized, right? These are the eigenvalues of that matrix. So now we know its inverse, right? It's just 1 over that. It's still diagonal, it's just 1 over that. And now we know the correlation function.
But between phi 1 and phi 2, phi 2, but not between phi.
Come on. Come on. Of course, if you know between phi 1 and phi 1 and phi 2, you can extract whatever it is between phi and phi. Of course you can extract. Okay, so let me write down now so let me write it like this. Phi tilde of k, phi tilde of k prime is the complex guys, okay? So what will this be? Okay, I claim that this has to be again just the inverse of that matrix, okay? So what is the inverse of that matrix? Well, first of all, I have to make sure that it's diagonal, okay? So I'll have to put something that looks like k1 plus k2, 0, product of delta of that, okay? And then it will be just k1 squared plus m squared.
Just make the link inside K1, K2.
Okay? Good. Right, does everybody believe this? There's a little step in going from that to here. Okay, because you have to go to 500, 5.2 and come back to 5. I'm sure you figure it out. Alright? Okay, good. So now that we have it, now we can easily figure out what is the correlation function in terms of x. Right? So now what I want is I want phi of x, phi of 0 in real space. Right? So what will this be? Again, there will be some sum over k1 and k2. Right? And then there will be a 1 over L to the d over here. Right? And then there will be this, let's see, d to the I k1 dot x, right? And nothing because it's 0 on the other one. And it looks like phi tilde of k1, phi tilde of k2. Right? That's it. Alright, so now I'm going to use the value of that I already have. So k2 is going to be minus k1. So I'm just going to call it k. So it looks like 1 over L to the d, the sum over k of that's what it is. Okay? And now it is convenient to convert this sum into an integral. So you know that the spacing between the k is 2 pi over L. So this thing basically is the same as integral okay? Good enough? Alright, now this is all still mean field theory because there are no interactions, right? And you're sitting for t bigger than tc. And so now we want to figure out what happens as you approach. Okay, what is the correlation length? How does it diverge as you approach? Alright, so remember this m squared was r, right? It was t minus tc, proportional to t minus tc, up to some constant. Alright, so now I want to actually look at the behavior of this as a function of x. It's very easy to see that it doesn't depend on the direction of x, right? It's sort of obvious because this guy is a scalar. I can rotate x and I can rotate k, right, on the d sphere. It's going to be the same. So I might as well take x to be in a particular direction. Let us say in the 1 direction. Okay, so if I do that, then you see what I have is something that looks like this. So I have the integral dk2, dk3, and so on up to dkd with some factors of 2 pi. And then I have this minus infinity to infinity dk1 over 2 pi d to the I k1 x, right? This x is just the magnitude of x. And then there's a k1 squared plus all the other guys. So let me call them k parallel squared plus m squared, okay? These are all the other guys. Okay? Now this guy, you can do by contour integration. This has 2 poles. They're both imaginary poles, plus and minus the I times the square root of this guy. Right? You have to choose the correct pole when you do your contour integration. Right? You do all of that, and this integral boils down to something that looks like e to the minus k, sorry, e to the minus magnitude of x times the square root. Okay? Divided by the square root. Something like this. Okay? Good?
K is going to be equal to K1 square plus K11 square.
Well, yes, by 1, 1 I meant parallel. So let me call it perpendicular, okay? Maybe that'll make it not like 11. Okay? So in other words, I'm choosing one direction and all the other perpendicular directions. Okay, that's all.
K is radius vector in the K space.
K1 is
I'm choosing x in the one direction. Right? Okay? Good. So now I want to know what happens to this thing as I make x very large. Okay? So as I make x very large, basically this number becomes very large, right? So I can use the method of steepest descents to figure out what the answer is. Whenever I have an exponential with some very large coefficient, I can use the method of steepest descents, right? Basically, in this case, steepest descents tells you something very simple. It says that this guy is minimized when k perp is 0. So for large values of x, it's only very tiny values of k perp that matter. You can see that, right? Okay? So basically, this whole thing should go like e to the minus x times m, roughly speaking, up to some powers. Yes, agree? If you want to be specific, you can actually do it in a particular dimension and see. Because the problem is there's some difference between even dimensions and odd dimensions. Okay, in some dimensions, I believe it is